Let's consider second order accurate scheme. An example of this is E scheme. So the grid density in one dimension has to grow as kd power 0.5, and it basically an increased law of the number of grid points per wavelength. So here d is the characteristic size or diameter of the simulation region, k is a wave number. And therefore, the total number of unknown scale is kd power 1.5 in one dimension. In the case of two dimensions, scale is kd power 3. And in three dimensions, its scale is kd power 4.5. And a way to mitigate this growth in the unknown count is to use higher order method. Alternatively, we can also hybridize a differential equation solver with an integral equation solver when a larger homogeneity region exists. So in other words, we can combine a differential equation solver with an integral equation solver. And fast direct solver also exists to solve the matrix system resulting from differential equations. So we can solve the sparse matrices in the order of n square operation in 2 dimension and order of n power 1.67 operation in the 3 dimensions in our case. And basically the nested dissection order method permits the direct solution of the matrix systems in order of n power 1.5 operations in 2 dimension and n power 1.33 operations in 3 dimension. So the inverse of the sparse matrices is usually dense matrix. And a frontal algorithm can be used to greatly reduce memory storage and computer time in some applications. So now we are moving to the topic of convergence rate of iterative differential equation solver. And differential equation solvers, they are associated with sparse matrices with order of n elements, and therefore we can achieve a matrix vector product in order of n operation. So let's consider the case when we have an order of n elements, we perform the order of n operations and we solve the matrix system iteratively. As always, we aim to accelerate differential equation solver. So the only viable option for this is to reduce the number of iterations needed. And if we work with time stepping method, we aim to reduce the number of time steps needed. The condition number of the matrix determines the convergence rate of a matrix equation, and this condition number is a ratio of its largest eigenvalue to its smallest eigenvalue. And for Laplace equations, the equivalent matrix can always be positive defined, and it stems from the condition that the Laplacian operator is a negative defined operator for the case when we work with either homogeneous Dirichlet boundary condition and functions is equal to 0 at the boundary, or for the case when we work with a homogeneous Neumann boundary condition and a function's derivative perpendicular to the boundary is equal to 0 at the boundary. And so basically n it's the case when n multiplied by del phi r equal to 0. And we would like to briefly discuss that this Laplacian operator properties result from the following consideration. We can perform integration by paths, and we can see that this expression on the right-hand side is always negative. And earlier we discussed that the Laplacian equation is called elliptic. So Helmholtz equation is related to the wave equation and it's called hyperbolic. And we also discussed a diffusion equation, which is midway between elliptic and hyperbolic and is called parabolic. So we are looking for the eigenvalue of Laplacian operator, and it is equivalent to solving the following equation. And it is also the same as solving a resonant problem involving the Helmholtz equation. For instance, in the two-dimensional case, a Helmholtz equation is defined by this expression, and therefore the largest eigenvalue corresponds to the high special frequency supported by the mesh. This highest spatial frequency is proportional to 1 divided by delta square, and in this case delta is the discretization size of the mesh. And the lowest eigenvalue is the lowest spatial frequency supported by the region. So it's proportional to 1 over L square. And here L is a simulation region, and we often call it a characteristic size of the region. And therefore, the condition number of the matrix system is proportional to L square divided by delta square, and I hope you appreciate the beauty of this consideration in estimates. It's very approximate estimate, but we can get an idea about situation in general. So the number of elements n is proportional to L square divided by delta square, and the condition number is proportional to the number of elements n. To sum up this part of the information, we take the characteristic size of the computational region and divide it to the mesh size, and to estimate the matrix condition number, we can simply take power 2 of this ratio of the domain size over the mesh step.